Just got it. Okay, we're gonna start. This one, summer 18 question paper 2-1. Now, starting with the first part. And I'm going to be quick, TK. We're going to try and complete the whole paper, TK. Summer 18 question paper 2-1. TK. And starting with the first part, now he's saying sulfuric acid is manufactured by the contact process. One stage in the process is the conversion of sulfur dioxide into sulfur trioxide in the presence of a heterogeneous catalyst. So that's the contact process. State the effect of a catalyst on a reaction. Explain how a catalyst causes this effect. So what does a catalyst do? You just have to write 2-3 things. TK, that's basic O levels. Speeds up the reaction. You get more effective collisions with a catalyst. Why? Because it lowers the activation energy. How does it do that? Provides an alternate path. And at the end, it remains unchanged as well during the reaction. So state the effect, explain how the catalyst causes this effect. So we did mention that. You don't have to go into a lot of detail. There's a thing, state the meaning of the term heterogeneous as applied to a catalyst. So there are two types of catalysts. One is homogeneous, the other one is heterogeneous. So heterogeneous catalyst is that the catalyst and the reactants are not in the same phase. Basically, they don't have the same state. For example, in this reaction, it's a heterogeneous catalyst because all of these are gases. SO2 is a gas, O2 is a gas, even the product is a gas, while the catalyst, which is B2O5, that's a solid. So they're not in the same phase. Bond energies are provided. You're being asked to figure out the enthalpy change for this reaction. So what is enthalpy change? It's the amount of energy that is needed to break bonds. So bonds broken, that's in the reactants, minus the bonds that are going to be formed. So that is what enthalpy change is. So we're going to try and figure out this one. So how many bonds are broken? That's 2 bonds of S double bond O. So that is broken. So that is 534 times 2. And then 1 bond of O double bond O is broken. That's 496. And there's only one of that. So that's 1 times 496. And then how many bonds are formed? That's going to be exothermic. So that's 3 bonds. Actually, this is not 2. This is actually 4. There are 2 SO2 molecules. That's 4 double bonds that are being broken. And over here, you have 6 S double bond O's that are getting formed. 6 of them. So that is unknown. So that's X. That's what we want to find out. And the overall enthalpy change would be minus 196. So 4 double bond O's broken over here, 1 double bond O broken over here, 6 double bond O's, sulfur and oxygen double bonds getting formed over here. That is what is unknown. So you just have to solve for X. So what is X going to be? So it's going to be 4 times 534 plus 1 times 496. And then it's minus 196. Take the 6X, it's not going to be minus 196, it's going to be plus 186. If I take this on the left side. And then 6X on the other side, so that's, so I'm going to divide all of this by 6. So what are we getting for this? Umayyad, Muntasir.
471 रीचेक
470
करवा लें।
ठीक है 470
Yes, 471.
471 kilojoules per mole. ठीक है, I'm pretty sure that's going to be correct. Next one is, he's given you the contact process is usually carried out at a temperature of about 400 degrees centigrade and a pressure just above atmospheric pressure. Using a higher or lower temperature and pressure would affect both the rate of production of sulfur dioxide and the yield of sulfur dioxide. So he's saying that changing the conditions would affect the rate as well as the yield. A reaction pathway diagram is shown, and it's labeled. It's like an O-levels question. So complete a table by stating which letter A to E represents the energy change described. The energy change for the production of SO3. So which arrow is that? I mean, it's the overall enthalpy change for the production of SO3. Which arrow is this? क्या होगा anyone?
So is this the arrow for
B?
delta H, is it?
It's gonna be B, right? Okay, that's the net energy change of the reaction. Yep, P. Then you have the activation energy for the production of SO3 in the absence of a catalyst. So in the this one is going to be A. In the absence, that's the activation energy. That's the energy that is initially needed to break the bonds. So that's A. Or we'll pick here last. The activation energy for the first step in the decomposition of SO3 in the presence of a catalyst. So decomposition. So basically now I think he wants to go back. Decomposition means you're going to go back from SO3 all the way back to
D.
It's going to be D, because you're going in the reverse direction. And in the presence of a catalyst, so this is what a catalyst does, that it provides an alternate path. So SO3 breaks down to form something, and then that thing forms the products. So it's going to be D. That's the energy that would be initially, if you're starting over here, that's the energy that is initially needed, and that's D. Okay, is this clear? This thing?
Yes.
So then you have the next thing. Explain the effect of increasing temperature on the rate of production of SO3. So just the rate, increasing temperature. So higher temperature, what happens? More. Remember, you have to be very careful what he's asking. You have to. A lot of people misinterpret questions like these. So higher temperature, you've got more kinetic energy, and because of more kinetic energy, what is going to happen is that you're going to have more frequent and more effective collisions. Or successful collisions. Which is why you'll have a faster reaction. And now he's talking about yield. Now he's talking about equilibrium. So higher temperature, which side is going to be favored, exo or endo?
Exo.
Okay, so at higher temperature, it's going to be the higher temperature favors endothermic. So endothermic is favored, which in this case is what? Backward or forward? The forward is exo, so it's going to be backward hogi. So backward reaction speeds up and the yield decreases.
सर मुझे एंडोथर्मिक वाली बात नहीं समझ आई.
Higher temperature always favors endothermic reaction.
ये बस याद रखना है, इसकी कोई रीजन है?
Lee-Chatelain principle का rule है ना. Like if you increase energy, right, the reaction that needs energy, that will obviously speed up. Well, if there's a reaction that needs energy, right, and you're giving it energy, so obviously it's going to speed up. As an suggest an equation for the reaction of oleum with water to form sulfuric acid. So I think everything is given. So there's oleum, so it's the same as O-levels, with water to give you sulfuric acid, which is what? H2 SO4, and you'll just balance it. And balance it, 2H2SO4. That's I guess it is balanced. Next one. Complete the dot and cross diagram to show the bonding in the molecule of SO2. He already gave us the structural formula. I mean, this was previously drawn. So there's sulfur and there's oxygen. So this was already given. So what you have to do is you've got a double bond and you've got a double bond here. So you got a double bond over here. And you've got a double bond over here as well. So that's the dot and cross, but how many electrons are left for oxygen? Oxygen, remember, is in group 6. So how many electrons are remaining in its outer shell? Well, it's in group 6, so that means 2 electrons are being shared. So there are 4 electrons remaining. This oxygen is in group 6, that means 6 valence electrons, 2 are being shared. So there'll be 4 electrons that will be remaining. Sulfur, on the other hand, is also in group 6, but it is sharing 2 electrons over here and 2 electrons over here. So it's sharing a total of 4 electrons. So out of 6, only 2 electrons are left. So that's the dot and cross diagram of SO2. And then you have to tell what's a Bronsted-Lowry acid. So what's an acid? क्या होता है?
Proton donor.
ठीक है, so it's a proton donor, and I mean that's it. That's what Bronsted-Lowry acid is simply the definition of an acid. Strong means what? Strong means that it ionizes fully.
Completely.
ठीक है. Fully or completely. So it's an acid that ionizes fully and it's a proton donor. Write in the equation to show how the acid-base behavior of sulfuric acid with water includes state symbols. So sulfuric acid is an acid, so it's a proton donor. And remember, इसका मैं draw कर लेता हूँ water. For water, I'm going to draw the. Remember, water or anything that has lone pairs, it can act as a base. Why can it act as a base? Because if sulfuric acid loses an H plus 1, so it will become HSO4 minus 1. So out of the 2 H's, it could lose both H's as well. Right now, let's assume that it loses one of the H's. So it's acting as an acid. Where will that H end up? That H will end up with water, because water can accept and natively bond to an H plus 1. The lone pair of water can attract an H plus 1. So this is your water molecule, and that's your H3O plus 1 ion. So he told us to show how it acts as an acid, which we have. I mean, this is acting as an acid. This is acting as a base. And always remember, things that have lone pairs like nitrogen or oxygen, they are capable of accepting H positive ions. So next one. Next one is that he's talking about crude oil. So the question is, explain why I think it's a 2-mark simple question. Explain why the hydrocarbon molecules in crude oil have different boiling points. So why do they have different boiling points? First thing, hydrocarbon. What intermolecular?
Because they have different length of chain.
Okay, what intermolecular force? Firstly, what type of intermolecular force will they have?
Van der Waals forces.
Okay, so it's hydrocarbons, remember, are non-polar. They don't have any polarity. So they only have van der Waals. And van der Waals depends on size. So bigger molecules will have more van der Waals forces. And that's why they're going to have higher melting points and boiling points. Okay, so that's going to be your 2-mark reason for that. The next thing is some of the hydrocarbon molecules obtained from crude oil are processed further by cracking. Suggests why some hydrocarbon molecules. Why do you need to crack crude oil molecules?
Because the bigger ones are not usable and the smaller chains are more usable.
Okay, reason. What's the reason? What's wrong with bigger molecules? Firstly, bigger molecules are going to have 1 second. But to get, I think it's a 1-mark question, so that would probably be acceptable. But
So
I'm just
more
going.
viscous, less flammable.
Yes, bigger molecules have higher melting and boiling points, so they're probably solids or semi-solids. They will be less flammable as well. They'll be more viscous. While smaller molecules are therefore more useful. Smaller molecules. Why they process further to get smaller molecules? TK, they're more useful. Just a 1-mark question, so I don't think they'll be looking for the actual reasons why it is. But I mean, it's better to actually write a complete answer. So to extend the answer, it's just going to be that smaller molecules are more flammable. They are less viscous. They've got lower melting and boiling points. They're more volatile, so they'll turn into gases easily. It's a lot easier to actually transport gases through pipes, etc. Next part is, if we've got dodocane, it produces 2 moles of ethene and 1 mole of another hydrocarbon. So you just have to write an equation. So C12H26, it breaks down, produces 2 moles of ethene. So can you tell me what's this other hydrocarbon that's going to be produced?
C8H H18
18?
G.
Okay. The ethene can be used in the production of polyethylene. Give the full name of the process used to produce. What is the name of when you form a polymer of ethene?
Addition polymerization.
Okay, that's addition. Polymerization. So that's the full name of the process. Now, next part is give 2 reasons why polythene should be reused or recycled rather than just thrown. So polythene is just plastics, right? So why do you want them to be recycled?
It's hard to decompose and it's not good for the environment.
There's a word for that, hard to decompose. What's the word for that? It's non-biodegradable. Okay, so it non-biodegradable. So you need landfill sites. Burning produces pollution. So that's why it's better to actually, animals can choke together. That's another thing. Animals can consume and die on it. So you've got a displayed formula, you have to, it's an addition polymer. So you have to figure out what the monomer is. So all you have to do is you just have to identify what is the repeat unit. I mean, that's your repeat unit. So it's basically COOCH3 at the top, and you've got a CH3 at the bottom, and you've got a carbon next door which has 2 H's. Now this is the thing that's repeating over and over again. So that's your repeat unit. To figure out what the monomer is, just get rid of the connecting linkages and put the double bond back in the middle, and that's your monomer. But you have to draw the displayed formula. So in displayed formula, you have to draw every single bond. So this C double bond O and O is definitely an ester. So you have to show every single atom in a displayed formula. The bottom is CH3, so that's C with 3 H's. And next door there's 2 H's. And there's going to be a double bond. So that's what they were looking for. So next one. Now the next one is the element in the third period exhibit periodicity in both their chemical and physical properties. A graph of the, so I think this is all third period, right? It's the element as well as the ion, and they've plotted the ionic radiuses and the atomic radiuses. Explain the decrease in the atomic radius across the third period. So when you move across the period, why is the atomic radius decreasing?
Because the number of shield is same and the charge density is increasing. That's why.
So one thing is they have the same number of shells, because same number of shells. So it's constant shielding. But what happens with charge density? There's another word for that. What happens when you move across the period? You get more protons.
High charge density.
Nuclear charge.
ये दो different चीजें हैं sir, nuclear charge और high charge density.
But charge density is how concentrated the charge is. Nuclear charge is simply how much is the charge. So nuclear, I mean, you can write that. You can, in this case, you can actually write that. Okay, the charge density is increasing. Okay, obviously, you're getting more charge, and the atomic radius is decreasing. So nuclear charge, or the number of protons, or the proton number increases across the period. So that is why, because of the increased attraction, there's going to be more attraction. Proton number increases. So hence you're going to write that there's more attraction between the nucleus and the outer electrons, or the valence electrons. And your valence electrons. Now for sodium to silicon, the ionic radius are less than the, so why is the ionic radius of positive ions lesser?
Because they lost electron as their metals.
Not only did they lose electrons, they lost the entire outer shell. So they lost, when a positive ion is formed, they lose their outer shell electrons. That's it, 1 mark. Explain why for the non-metals, why are their ionic radiuses larger?
Because they are gaining an outer shell.
No, they're not gaining an outer shell. They're gaining electrons, which leads to more electron-electron repulsion. This is Cl, and Cl is not gain. Cl already had 7 electrons in its outer shell. But when it becomes Cl -1, it gains an extra electron, right? So because of these extra, it's not gaining an outer shell. The shell was already there. It's just completing its outer shell. But because there's extra electrons, there's more electron-electron repulsion. Electron-electron repulsion. Which is why the electrons are further away from each other, or further from the nucleus. Is this clear?
सर अगर इलेक्ट्रॉन ज्यादा हो रहे हैं, इसका मतलब प्रोटॉन भी एक एलिमेंट में ज्यादा हो रहे हैं, तो कभी कभार हम लोग इलेक्ट्रॉन की बात
इधर हम उस तरह बात नहीं कर रहे, इधर हम Cl, we comparing Cl with Cl ions. So they have exactly the same number of protons. It's just that Cl negative ions will, because they have a slightly more number of electrons, so they'll have greater repulsion in that case. So now the first, did we need that said? Now the first ionization energies of the elements across the third period show a general increase. Aluminium and sulfur do not follow this trend. Explain why aluminium has a lower first. So this is about the dips that happen when you move across the period. He's talking about the first ionization energy. So he's talking about both of them. So we can talk about both of them. When you go across the period, there's a dip at group 3, then it increases. Then there's a dip at group 6, and then it continues to increase, right? So why do we have a dip at aluminium? What's the reason for that?
It's in aluminium, the electron is moved from a high energy 2p subshell, which is further away from a 2s subshell and has more shielding.
So an aluminium electron is removed from a higher energy, p subshell. Which is more shielded. Compared to inner 2s subshell. Hence, easier to remove electrons. What happens at sulfur?
So the electron is removed from a paired p subshell, and the spin pair repulsion decreases the I.
Okay, so in sulfur, electron is removed from a paired p subshell. So there's spin pair repulsion or electron-electron repulsion. So which is why it becomes easier to actually remove. Remove electrons. Okay, just hold on 1 second. Yeah, just 1 second. I said, can you hear me?
Yes, sir.
Yes, sir.
I said this one, the elements in the third period. From sodium to silicon can react with chlorine to form chlorides. Stein explained the pattern and change of oxidation number, which occurs to both chlorine and the different PHC elements when they react together. So he's talking about the pattern. What is he asking? Pattern in the change of oxidation number, which occurs to both chlorine. From sodium can react with chlorine to form chlorides. So we need to discuss the pattern. So I think Na is what, I don't know how to write this one. Na is +1. Mg would obviously be +2. Al forms a AlClC, so that's +3, right? What comes after that? Silicon forms SiCl4, so that's +4. Phosphorus forms PCl3 and PCl5. He just wanted till silicon, so I guess up till silicon, that's it. And then he's saying, so that's the pattern. It's a 3-mark question. So first, the pattern is, the trend is that the oxidation number increases. That's the pattern, that's the trend. So you're going from +1 to +4. And what else is he asking? We have to be very specific about. State, explain the pattern which occurs to both chlorine. So what happens to, we have to discuss chlorine as well. Chlorine remains -1 in all of them. So I guess that gives you your 3 marks, I think. That's it. That is exactly what he was looking for. As the next one is, give the equation to show the reaction of sodium chloride and silicon 4 chloride when separately added to water. So the first one, NaCl, it only dissolves. So when you mix it in water, nothing happens to it. NaCl solid plus aqueous, it's going to dissolve. It's going to form sodium ions, aqueous, and Cl ions, which are also aqueous. Silicon chloride, on the other hand, SiCl4, what does it do? I'm just going to, what does silicon chloride do? When you mix it in water, what happens?
Silicon hydroxide with HCl.
So HCl, fumes of HCl gas, white fumes of HCl gas are going to be formed, and you're going to have a vigorous hydrolysis. So this is what will happen. SiCl4 plus water, that will form silicon hydroxide or silicon oxide plus HCl. Aluminum chloride, silicon chloride, PCl3, PCl5, they all have vigorous hydrolysis, and they all form HCl gas when they react. So this one will be with water. SiCl4 is a colorless liquid. It's going to form silicon oxide or silicon hydroxide and HCl. Now complete a table to describe the structure and bonding in NaCl is ionic. Structure is, it's a giant ionic lattice. So over here, I think we just write giant lattice, or in bonding, we're going to write ionic. Silicon 4 chloride is a simple molecule. It's silicon bonded to just 4 Cls, that's it. So this is simple molecular. And the type of bonding is going to be covalent.
Sir, I know it's a basic thing, लेकिन मुझे ये नहीं समझ आता कि कब giant लिखना और कब simple molecular लिखना है, मुझे उल्टे लगते हैं.
नहीं देखो, it's one thing is कि it's ionic, they're all giant. ठीक है, whenever it's an ionic compound, metal and non-metal bonded together, it's always a giant lattice. Na+1 attracted to Cl-1, Cl-1 attracted to Na+1, and so on.
Okay. And about other?
Covalent, when it's two non-metals, covalent compounds are mostly simple molecular. Like 99% of them will just be simple molecular. In your course, there are very few that are actually giant covalent. Giant would be diamond, graphite. silicon, silica, SiO2. These are the ones that are giant.
Got it.
Agar metal hoga na, if it's a metal is also a giant metallic lattice. It's also giant. So they also happen to be giant metallic lattices. As the next one is, this is organic chemistry. So this one is there's a molecule, it's an alcohol. The reaction between X and alkaline aqueous iodine produces a yellow precipitate. Give the name of the compound formed as a yellow precipitate in the reaction. So first, the reaction between X and alkaline aqueous iodine produces a yellow precipitate. So first thing is, who produces a yellow precipitate? If you look at your organic notes, just a second, okay, this one. We're dealing with an iodoform test. So the iodoform test is this one. This one over here, that's your iodoform test. The iodoform test is positive when you have a methyl, which is either next to a carbonyl, a ketone or an aldehyde, or you've got a methyl, which is next to CHOH. So we have to look over here and we have to see if this is something which has a similar structure. So we've got a CH3 and then we have CHOH. And after that, we've got CH2 and we've got CH2. And then you have, one second. And then you have CH3. Now, so it is a structure.
Yes, it will.
It will. So it is a structure which has CH3, CHOH, right? And what's going to happen next? The CH3 will break off and it will form a yellow precipitate of CHI3, and the rest of the carbon will turn into a carboxylic acid or a salt of carboxylic acid, since you have an alkaline condition. So the carboxylic acid formed, this carbon over here will turn into a carboxylic acid, but it will form a salt because it's alkaline condition. So it will, this thing over here will break at this point. So the yellow precipitate will be CHI3, that's your yellow precipitate. He's talking about the yellow precipitate, so give the name of the compound, that's triiodomethane. And the rest of the molecule, it's going to be CH3, CH2, and that particular carbon will turn into a carboxylic acid, but a salt of the carboxylic acid since the conditions are alkaline. You also have to give the name of X. What is the name of X? 4 carbon atoms. What would you call 4 carbon atoms?
Butanol.
Yeah, but what is the position of the alcohol?
2.
So it's butan 2-ol. Now he's saying that 3 structures, structural isomers of X that are alcohols draw the structures of these 3 compounds. So we have to draw, I think, 3 other structures. So we can either draw positional isomers, so the OH could be on the carbon at the end, or
branch for carbon.
It could be branch, so you could have an OH at the end, or you could have OH on the middle carbon atom. The rest are all H atoms, so you can draw all the H atoms. You can write it yourself. This one will have 3 H's. This one will have 3 H's, 1 H, 2 H's. This one will have 3 H's. Then he's saying we just had to draw them. Then there are 2 reactions which are given. Identify the type of reaction involved in reaction number 1. So how does an alcohol turn into a ketone? Like, what is this reaction?
Oxidation.
Okay, that's oxidation. And that's oxidation of a secondary alcohol. A secondary alcohol turns into a ketone. What are the reagents? It's either KMNO4 acidified or K2Cr2O7 acidified and reflux. So that is what's going to do that. So identify the type of reaction, that's oxidation. He's also asking for the reagents. So the reagents are going to be K2Cr2O7 acidified. And the condition is going to be that you have to reflux. So it will turn into a ketone. Next part is reaction number 2 can be carried out by passing the vapor of X over hot aluminum oxide. The product of reaction 2 is C4H8. It's actually a mixture of 3 isomers. Give the full names of the 3 isomers formed. So he's saying this is hot Al2O3. And it's turning into an alkene. It's clearly an alkene. It's clearly an alkene. So firstly, what exactly is this reaction? Okay, it's turning into an alkene. So it's this reaction. It's called dehydration. Alcohol turning back into an alkene. That's Al2O3 plus heat or SiO2 plus heat. So you'll get an alkene. So what will happen is the place where you had an OH, you'll have a double bond now. So if your molecule is this one, you had an OH over here on the second one. So if dehydration happens, the OH will go and this carbon will have a double bond, but you've got 2 options now. Either the double bond will be on the left side or the double bond will appear on the right side. So you're going to get 2 different types of alkenes. Let me add the H's. These are your H atoms. So you're getting 2 alkenes. Why did he say you're getting 3 alkenes? Like the double bond is either going to be on this side or it's going to be on the left side. So why did he say that he's getting 3 alkenes? Like, how is this 3 alkenes?
Because the second one जो आपने आखिर में बनाया उसका I think cis trans बन सकता है.
Okay, this one will have cis and trans arrangements because it's got 2 different groups. There's an H and a CH3 on one side. So it's got a cis arrangement and as well as it's got a trans arrangement. So you have to write the names of these molecules. What's the name of this molecule, the first one?
Butene.
1-ene.
Okay.
Double bond is on the first carbon atom. What is the name of the second one? That's butene. And there'll be 2 versions. One will be cis butene, and then there's going to be trans butene. So you're going to have 2 different versions for that. Over here, you're being asked to draw the mechanism for electrophilic addition. So firstly, it's an unsymmetric alkene. The H is positive. The Br is slight negative. The positive H will get attracted to the electrons in the double bond. The electrons in the bond over here, they're going to be repelled. So double bond electrons are going to be attracted to H, and the Br is going to get knocked out. So the Br gets knocked out. So you get a Br -1. Now you've got a CH3, a carbon, and a CH3 at the top, and you've got a double bond and 2 H's. Now the positive H is coming in, and it's going to take away the electrons over here. So will it get attached to the right side or the left side? In electrophilic addition, where does the H get attached to?
Right side.
Okay, so the rule is, Markovnikov's rule is that the H will get attached to the carbon that's already bonded to more H atoms. And this carbon over here will become a carbocation. And the Br -1 is going to then go and attach itself to this carbon. So that's going to be 2 bromo, 2 methyl. propane. I mean,
लेकिन सर जो ड्रॉ करना है वो भी हमने मेजर ही ड्रॉ करना है, माइनर पे मार्क्स नहीं मिलेंगे।
based on this, I mean, you could have checked this molecule, right?
Mhm.
So the bromine is getting attached to the second one, right? So it's getting attached to the second one. So not in the
Okay.
first one. So from that, even it's, I mean, this one is, they've drawn the major product. Okay, so remember the rule is, for a major product, the rule is that the H has two choices. It can attach to either one of the carbons, but the rule is that the H likes to get attached to the carbon that's already bonded to more H atoms. So it's going to be on the right side. Now the next thing is, one second. Now he's asking you to justify why that's the major product. One second. Now he's asking you to justify why this is the major product. So the reasoning behind the Markovnikov's rule, remember, it's always a 2-mark question. So you have to justify why forming this carbocation is easier. So what kind of carbocation is this? Is this a 3-degree carbocation, a 2-degree, or a 1-degree? Is this a primary, secondary, or tertiary?
Primary.
Nee, kitni carbon chains? How many carbon chains? It's got 1 carbon chain over here, 1 over here. So remember, 3-degree. So it's a tertiary carbocation. 3-degree carbocations, remember, are easier to form, are more stable. Then you have to explain why. The reason is, as they have more electron donating alkyl chains. So as they have more electron donating alkyl chains. And since they have more electron donating alkyl chains, hence they will have a lower charge density. So basically the in-depth, it's just a 2-mark question. It's always going to be a 2-mark question. A 3-degree carbocation is always easier to form because it's easier to steal electrons from the double bond, because the positive charge is going to be very small. When the H took away electrons from the double bond, the positive charge was very small. So it's easier to form a positive charge that is smaller in size. So it's easier for H to steal electrons away from it. That's why the reaction happens. If the positive charge had been large, then it would be very difficult for the H to steal electrons from the double bond. So the reaction would not have happened. So always remember that that a lower charge density carbocation is the one that has more electrons surrounding it, that has more alkyl chains. So a 3-degree carbocation is always going to be more stable. And that's it. It's just a 2-mark question. TK, you always have to explain it this way. You clear this one?
Yes, sir.
So TK, we're done with the paper, TK. So we've completed this one. So tomorrow we'll try and do another one. इसको मैं save कर लूँ ज़रा. ठीक है. So ठीक है, everyone.
Sir, I had a question for part C, part 2, sir.
इसी paper का this one?
Yeah, same paper.
4 part C. This one?
For the yes, sir. For the reagents, is it Al2O3 and also concentrated sulfuric acid, sir?
No, this one, reaction number 2, you're talking about, right?
Yes, sir. Reaction 2, yes, sir.
So it's basically or concentrated sulfuric acid.
Oh.
Even
either one, is it?
Either one. Even with Al2 SiO2, it's either it could be both. It could be any one of them. Even that will work.
Okay, sir. Okay.
ठीक है.
Thank you, sir.
Okay, take care.